And we're going to, this next session will be real-world application of GRIDSMART detection system for ATSPMs. ATSPM, automated traffic signal performance measures. ATSPMs show real-world, real-time historical functionality and signalize intersections, and allows engineers to directly measure what they previously could only estimate and model. ATSPMs allow agencies to effectively optimize managed traffic signals without extensive field data collection, and to visualize data in an easy-to-understand format that is web-based and easily accessible by a diverse group of users. Using ATSPMs, agencies are able to improve mobility, increase safety, and use resources more effectively. Daniel A. Johnson is a supervising ITS traffic engineer for WSP in Charlotte, North Carolina. Daniel is a professional engineer and IMSA traffic signal senior field technician level 3. Andrei Dumitru is a North Carolina professional engineer serving as the traffic engineer and operations manager for the City of Concord, North Carolina. His area of expertise is an intelligent transportation system deployment and integration. Welcome to Intersect, two of the country's most respected traffic experts, GRIDSMART proponents, Daniel and Andrei.
Thank you, everyone, for the opportunity to talk to you today about ATSPM and how the City of Concord is using ATSPM and how we're using GRIDSMART as a building block in between the ATSPM software and then delivering data to the controller. So I started my career in the transportation market as a city traffic engineer for the City of Concord, ironically. And in that time, I learned from my superiors, the people I reported to, of who the customer was. The customer is the public, but it's the traveling public. It's not the taxpayer. We're not worried about the taxpayer. We're worried about the people that travel through our municipality, and we want them to be able to travel efficiently and effectively through the municipality on a daily basis. So the City of Concord has two pretty significant features in North Carolina, in the Charlotte, North Carolina area. It has Charlotte Motor Speedway, which you guys are from, and we're in the Tennessee market. It's a Bristol racetrack, is a great NASCAR racetrack. I got friends from Richmond that are here. Richmond Motor Speedway is a great racetrack. So 2 to 3 days out of the year, Concord becomes one of the largest cities in the state of North Carolina. And then after that day, we're just back to 80,000 population with the transient kind of travel throughout the municipality. We also have a Simon Mall that is labeled as the #1 tourist location in the state of North Carolina. It moves about 22 million people per year. So that's one of the largest traveled corridors in the state. So we manage both those two entities. They just happen to be on opposite sides of the exact same corridor, which makes it very challenging. So what I did as an early traffic engineer is I had to understand, #1, traffic signals, but #2, how do I evaluate whether or not I did a good job? And the way to do that at the time, leading up to the point where this ATSPM stuff came about, is we would look at volume data and occupancy data. And then we'd throw all that mesh into the voodoo crystal ball, and then we'd look at it and we'd say, yeah, we did good, or no, we didn't do good, and we need to make changes. And then we had to look at that volume data again to determine if the changes we made were actually quality changes. And that was very difficult. That would take hours per day. I would pull detector data out of a master controller remotely through a dial-up modem. This is in 2008 to 2010, so not too long ago. Format that into a spreadsheet and then get some line graph. And I would spend hours doing that every day. And then this thing called ATSPM comes along, and now the controllers have the ability through standard open source data packet to give us arrival on green, or start of green, start of yellow, start of red, all detector information, and then we have the ability through some software package to plot that on a graphic, and we can make decisions very, very quickly. So the days of spending hours and hours analyzing data are really a thing of the past. So if you're doing it that way, you need to see that there is a mechanism forward to not have to do it that way. And that's what we're going to try to talk about. We're not going to get deep into ATSPM. We're going to talk about the peripherals of it. A lot of people talk about ATSPM in a very high-level way. We're not going to talk about the reports per se. We're going to talk about how do we get the data into the software. That's the hard part. Because you got building blocks. You got the software, you got the detection system, and you got the controller, and you got the network. We're going to try to connect those pieces together for you. So this is going to be a very technical session. A lot of sessions up to this point have been very high level. We're going to try to get right at the surface of the weeds, and if you have questions that get you down into the weeds, we will go as deep in the weeds as you want to go. All right. Ooh.
So now that you heard everything about ATSPMs from a electrical engineer that used to act as a traffic engineer, now you're going to hear from a computer and electrical engineer acting as a traffic engineer. So what's funny is that I remember when I started in this position that I was interested in the domain and started looking, and I've heard this terminology, and I was like, ATSPMs, like, what is this? And now, alongside with DSRC and 5G, it has become, in the last 3 years, basically a buzzword, right? And sure enough, a lot of people actually use it, but very few people integrated, built the whole system from the ground up, and basically configured everything so they can get data in such a way where a traffic engineer or a signal timing analyst can actually use it, right? So what we're talking about here is, today is ATSPM, what are detection requirements and reports, what are the needs and challenges, and then we're going to talk about detector management and hardware configurations, which Mr. Johnson is actually an expert in. So what is ATSPM as a concept, right? So automated traffic signal performance measures. They're ATC controllers that are collecting high definition data, so high definition as in every 10th of a second. And then we're all doing this cycle by cycle. We're getting detections, we're getting exactly what Daniel mentioned, star green, yellow and red periods, and preemption data, if available. Now, in order to make use of this, you need an ATSPM software package or system or implementation, however you want to call it, that collects, organizes, and reports the data. Now, very important is the fact that everything, all these reports, the majority of these reports are actually dependent on the detector data and on the type of detector data and on the amount of detector data. So let's look at basically what types of reports you get with what type of detection. So this chart, we're going to break it down in multiple pieces, but suffice to say, this is the end-all be-all, right? So this is the blueprint for what can you get from what you have. So say you have control logging capabilities and you have no detection. Are you still able to get something? Sure, of course. You're able to get what is called the phase termination chart, which is illustrated in the bottom right. You're able to get the split monitor data and see exactly what your splits were, what ran in that specific time period that you're looking at. You're able to get pedestrian delay, and then you're able to get preemption details, again, if available and if implemented. Now, that's ground zero, right? No detection. So what happens when you add in stop bar detection? Well, when you get stop bar detection, you can get access, you can unlock, right, the produce split failure, which is a chart that depicts how your split ran and if you still have a remaining queue in that specific detected region. Now, this is important, and for North Carolina, we have a standard detection layout template that calls up for stop bar detection on the side street, and that's all fine and dandy. But the moment you get more data, then you can actually populate a whole lot more charts, such as front of stop bar detection. That unlocks the turn and movement count data. So, which is illustrated in the table view up top, and then illustrated in a graphical view down at the bottom. And then, with advanced detection, you unlock the rest of the metrics, which in this case are the Purdue coordination diagram, the approach volume, arrivals on red, and the approach delay. Now, obviously, with advanced, so historically, advanced detections were always giving us the volume, right? Which in this case is important, but corroborate that with what we had before, with all detection that we had before, we're able to actually get the holy grail of metrics from a traffic signal coordination point of view, which is the Purdue coordination diagram. So this very intensive chart graphic depicts a couple of things. One, it depicts the arrivals on green as complementary with the arrivals on red. It depicts the individual arrivals, vehicle arrivals, as depicted by the blue dots on the chart. And then it gives access to one of the most important metrics that coagulates all these metrics for one singular intersection from a coordination standpoint, which is the platoon ratio. The platoon ratio, which is, think about it as a scorecard of the intersection of how it does in relationship with the other intersections on your corridor, where over a 1, you're doing fairly well. Over a 1.3, you're doing well. Over a 1.66 all the way to 2, you're doing amazing. So what you're going to see over here is our specific implementation looking on a specific time slice, how we're isolating the detector actuations, and how we're looking at an approach, at a southbound approach on one intersection on a 3-hour time slice, and we're looking at all the collected data in that day, and now we're able to see how we're doing in relation to the traffic signal coordination plans at that specific location. So what do you need for this? Well, you need the software. Everyone by now probably knows about the open source implementation, the UDOT and the GDOT implementations, but there are also proprietary custom solutions developed by large entities, large companies such as Econolite, but there are also other alternatives, such as the one that we use. In this case, a cloud-based ATSPM solution. You need ATC controllers. You need detection systems that the more detection, the better, obviously. And that's where GRIDSMART, the GRIDSMART solution comes in for us and an actual understanding of the platform that you're dealing with. Is it the NEMA world? Is it the Caltrans world? Or is it the ATC world, basically? So we're going to talk about an actual case study, test bed implementation, basically. One of the first locations where we implemented this in the City of Concord. It's an intersection that's quite expansive, that has dual through lanes, dual lefts, right turns, which in a normal North Carolina setup would have 26 detectors, which give you quite a lot of data. But can you obtain more? Can you get all the metrics that you need in a different type of implementation? How many detectors would you need to get all those metrics and get an encompassing view of your intersection? Well, a full ATSPM detector layout requires 60 detectors. 60 detectors, a lot of loops to cut. So that's where Daniel is going to come in and talk about how do we manage this challenge of the 60 detectors.
Thanks, Andrei. So we can see by the table, or by the graphic, the red squares that we've laid out. So we have front of stop bar per lane. So number one, let's say individualized detectors. So 60 individualized detectors. Front of stop bar for left turns and through movements and right turns. Presence detectors for each lane, left, through, and rights. And extension loops for each lane so that we can get that Purdue coordination diagram at the very end. So this is the granddaddy. This is we can get all the reports if we do an implementation like this. And so when you buy ATSPM software, if you don't have a detector assigned to a particular report, that report is grayed out and you can't even see it. If you look at the GDOT solution, UDOT solution, you'll pull up an intersection that's got 4 reports. You'll pull up another one that's got 10 reports. And it's dependent upon how much detection you have actually mapped to the software. Now, not all of these detectors are sending calls to phases. I think it's very important to say that up front. And we have to manage that from a traffic operations standpoint. We don't need every stop bar presence detector or front of stop bar detector to call a particular phase. So we're going into the controller and turning that off. That's why it's very important to understand the platform that you're working in. Obviously, it's an ATC controller. That becomes platform agnostic when we start talking about TS1, TS2, Caltrans, and how that software integrates with those cabinets. But in the end, we're trying to figure out how to manage 60 detectors. So the first thing, and that's the challenge, how do we manage 60 plus detectors? The first thing we have to do is kind of create a layout, which you just saw. Then we have to come up with a numbering system to connect the individual detectors to the detector inputs that are going to come into the controller. And then in our documentation, we need to know the approach, direction, what it's used for, is it presence, is it extension, and we're going to program all that into the ATSPM software so that we get all the correct metrics in the reports. So here's an example of how we numbered it. I know this is a test on the eyes like earlier, and this is a much better test on the eyes because I blew it up and it's kind of fuzzy. So in North Carolina, NCDOT is a Caltrans state. We're using Caltrans 332 cabinets. How many people are Caltrans cabinets in their municipality? So we're TS1. It's point-to-point, end-to-end wire from the controller to the output. It's basically a TS1 cabinet in a rack. So how many TS1 people we got in the room? How many TS2 people do we have in the room? How many ATC people do we have in the room? I know the VDOT guys are going to raise their hands. So you got a lot of platforms. So you got to understand what are the limitations or the advantages of those individual platforms, and then how do we overcome the limitations? So again, here's the numbering system. And in North Carolina, we're just going to use phase 6 as an example. The the actual phase 6 numbering system that connects from the cabinet to the controller, the 1's position number is the phase, and the 10's position number is the increment. So you'll see phase 6 front of stop bar is 6, 16, 26, 36, 46, 56. So I know when I pull that chart up, or if I have a detector failure and it's a 56, I know that's an extension loop based on the fact that I've got this layout, that it's an extension loop, number 5, blah, blah, blah. Now, one thing about the Caltrans cabinet in North Carolina is we have dip switches. Well, those dip switches are hard-coded to specific detector inputs, and on the even phase, it's going to be 26. So we set 26 to call a particular phase, so then when we hit the dip switches all work properly. So if you're in TS2, you're going to have to understand how to do that in TS2 so your test panel still works correctly, because we're going to max out our detector load. So you still want all those button push detectors to be accessible to the technician so they can debug it if they need to. So that's where you got to think through this numbering system. So we've created a spreadsheet, and we can share this. If anybody wants the spreadsheet, wants the layout diagram, we're more than happy to share any of that, and you can adapt it to your needs. So the left column, most column, is 64 individual detectors, because that's what a standard TS2 type controller can give us. If it's an ITS ATC controller, it'll have 128. We're not trying to get into that world yet. We're just trying to manage 64 at this point. So we have the detector number. This is what the controller sees. This is also the number that we put on the previous screen. And that's how we're going to map it in the controller. You'll notice that I've got a column for the BIU. How many people know what a BIU is? Bus interface unit. Now we're talking TS2 for all you Caltrans TS1 guys. And I'm going to explain that in a second. For the Caltrans people, we've got a slot, then we've got upper and lower. We've got standard NCDOT phasing or detector assignment. That's something that you'll change relative to your state, because GDOT is 1, 2, 3, 4, 5, 6, 7, 8. North Carolina is 1, 2, 12, 32, 42, 22. It's very different. You got to understand your state's or your locality's approach and how this stuff gets set up. Phase number, if it's going to call a phase. Approach, direction, that's very important for ATSPM. What the detector is it left turn through movement? Is it right turn? And then presence versus count, the size, kind of give or take. The position of it, because we're going to need to know that for ATSPM for some of the timing stuff that's in there. And then here's our switch buttons. So I went ahead and put the switch buttons in the diagram or in the spreadsheet, so I know I don't want to turn those phases off. I've got to be able to manage those test buttons and test switches in the numbering scheme. So this is kind of the backbone of the whole thing. So what are the limitations? All the TS1 guys out there. The TS1 is dependent on how many detector inputs can go through the A, B, C, and D connector. The TS1 cabinet will take, you can have 4 racks of 64 detectors in the cabinet, but it will combine them all down into phase 1 through 8. You cannot get individualized detection through a TS1 cabinet. It won't work. But that doesn't mean you got to change your cabinet out. We're going to get there. It's just a limitation of the platform. The TS2 guys, you got the best of both worlds. If you've got 4 detector racks, you can get 64 detectors through the serial data bus inside the cabinet. And the controller, and the cabinet and the controller can process individual detectors. I can cut 64 loops. I can run 64 individual loop leading cables into my cabinet, which is a lot. That's a lot of copper. And I can get everything with loops. But that's still a very cost-prohibitive solution. In the Caltrans world, we're kind of in the same boat as the TS1 guys. We only have 28 physical detector inputs in the cabinet. We can't get any more. The C1 connector will not, you got to jump into the C11, you get another 12, and that's all you got. So that's our platform limitations. Oh, I went back instead of forward. So this is what I'm dealing with, all you Caltrans guys. This is our detector rack. This particular cabinet and this cabinet have, this one might have only one detector rack. I don't see a lot of 336, so forgive me. This rack only gives me 28 detector inputs. So that's a bit challenging from a loop standpoint. So then, how does GRIDSMART interface in with these different platforms? Well, when you order your GS2 device, you're going to get the option to request a COM module. You can get a TS1 COM module, and you can hardwire from the GS2 device into the back plane of the cabinet, which can be very challenging if you don't know what you're doing, but you're still limited on your number of inputs. Okay, in your TS2 environment, we're just going to tie it in the SDLC, and we're all good. So really, the TS2 guys right now are kind of ahead of the game. It's all natural for them to just connect the GS2 into the SDLC bus, and then it's a factor of mapping detectors and understanding how to map those detectors around. So TS2 guys are in a good spot. The Caltrans guys, or sorry, I do have ITS on here. ITS or ATC cabinets, you've got a 25-pin module for the GS2. You go 25-pin and 25-pin to the ATC cabinet back rail, and you can get 128 detectors that way. So ATC guys are in good space as well. And when I'm talking about these SDLC cables, let me jump to the next slide. I'll go back one. And then you have hybrid solutions. So hybrid solutions are utilizing video detection in a way that some people are really not comfortable with, which is using a serial bus type interconnect between the detection system brain unit, the GS2 in this case with GRIDSMART, and the controller itself. So we're going to send detection across this serial data bus even though we may not have a TS2 cabinet. And that's the solution. That's what's going to help us bridge between those guys that have TS1 cabinets, those in my space that have Caltrans cabinets, and the TS2 guys. We're going to run all this heavy detector load across the SDLC. So how does a 2070 controller do that? It doesn't have a port 1 on the back. All you NEMA guys that got the box, it's got a port 1 on the front. That's pretty straightforward. But the TS1 guys are a little bit hesitant at that, I'll bet. You're not used to running things in this hybridized form. So here's some pictures of the Caltrans setup. So what I have is I've got a GS2 upper right-hand corner and a standard 2070 cabinet that's retrofitted to ATC. When I turn it around, you'll see it. And I've got basically an interconnect cable and the camera for the pleasure of having the camera on the screen. So on the 2070, for those guys that are Caltrans, there actually is a serial bus connector on the back. I didn't know that was there. I'll be completely honest. And then all of a sudden, it's like, I really started reading the specs and understanding how the software works. And it's right there as a C12S. It's also a C13S, so you actually have two 25-pin serial bus interconnects on the back of a 2070 controller that you can use to connect directly to a detection module like a GS2 device. So on the front of the GS2, we're using the standard 15-pin TS2 connector. And then to connect it together, we're getting a 15-pin cable to a 25-pin cable directly from GRIDSMART. You're shaking your head, yep, that's the way to do it. So for the NEMA people out there, we have a rack-mounted NEMA controller. I'm just going to show you that. This is we're in a Connellite state, so forgive the branding. This is a rack-mounted NEMA Cobalt. This was actually our first solution because at the time, the state was not allowing us to put a C1 module in a 2070 controller running a certain kind of software. But they would let us put a Cobalt controller in as a complete solution and then interconnect that with our video detection system so we could use this TS2 SDLC data bus. So this is the port that's on your NEMA controller, the port 1. This is a TS2 module on a GS2 connected to a port 1 on a NEMA controller. So if you have TS1 cabinets and you need more data and you want to set up more detectors and you've got GRIDSMART, just sitting there. You have the ability to configure it in this way and not have all those wires going to the backplane. Tear all that stuff out, contact your distributor, get an SDLC, a TS2 communication module, and connect it with a 15 to 15 pin connecting cord. Then it's just a matter of setting up your controller to bring all that data in. So the GRIDSMART setup. So now we're not, so for TS1 guys, you're probably setting it up, hitting the TS1 button, and you got two pigtails coming out of the GS2 wiring into the backplane. But again, you're only getting so much data and so many detector inputs in your controller. So what we're doing is we're setting it to TS2. We're utilizing a TS2 comm module. And then once we go in and set up the detectors, sorry, my laser pointer doesn't really work here. Then when you set up your detectors, when you do this drop down, now you're selecting the BIU you want it to output on. One is going to be detector 1 through 16 because each BIU manages 16 individual detectors. When you're on BIU 2, now we're in 17 to 32, and we're just selecting BIUs and placing our numbers. We already figured that stuff out in the spreadsheet. That's pretty easy. You're just going to draw your zone, connect your zone to a BIU number, right? In the controller, in the TS1 environment, all the ATC controllers are required to have some way of turning off and on the port 1 configuration. So the only thing we're going to turn on in the controller is the detector BIUs to be able to use them. We're not doing the TNI BIUs. That's the area that drives the load switches. So in TS1 and Caltrans, we're still going to send our outputs out the C1 connector or the A, B, and C connector by not configuring it for TNI BIUs. Does that make sense? For the TS1 and the Caltrans guys in the room. But we are going to turn on detector BIUs 1 through 4, so now we have digital serial input of 64 detectors between the detection device and the controller. And that's pretty simple. So now we're going to go into kind of some live setup environments in the City of Concord to show the different ways that GRIDSMART can be applied.
So, start off with a couple of implementations of single cameras, but then due to the footprint of the intersections that we have, we realized that dual cameras are a little bit better for the realm that the intersection covers. But those types of setups have some limitations as well, so that's why we ended up having hybridized solutions, where you have the GRIDSMART camera or cameras and using the 300-foot loop detectors. So one of the solutions that you guys see over here is a single dome camera with 2 advanced cameras at this intersection that's actually right now in a complete revamp. Would it have been nice to have 2 dome cameras and 2 advanced cameras? Yes, but unfortunately the system does not allow that. That's one of our pet peeves. But does it work? Yes. Do we still get a wealth of data with it? Yes, it does. Yes, it does definitely yield all that data.
I mean, you're getting every report out of that configuration,
yes,
right?
Yes, yes. So there is not even one single metric that we're not getting, with the caveat, obviously, that the Purdue coordination diagram is available only for the main approach. Now, the other poster child for our deployment is the intersection that you guys have seen before in the configuration, and with the 60 detectors, where we actually have 2 dome cameras. Unfortunately, we do not have any loops over there. The amount of copper that would need to be ran in for that intersection would be fairly interesting, to say the least.
Just as a note, if you don't mind me saying, This was originally a video detection intersection that had 6 directional video detection cameras by another vendor. And one of the challenges with that particular vendor is when their product life cycle ran out, we were no longer able to transition from a TS1 style integration to a TS2 integration. So they were going to require us to financially upgrade all 6 of those cameras to get the new module. And when we priced that out, it became cost prohibitive to stay with the same vendor. So we looked at GRIDSMART as a solution for this intersection because it was cost accessible to be able to do a 2-camera solution, and it was much easier to deploy with just a 2-wire system. So even though there are some extension loop limitations, that's kind of the background on how this particular intersection became an example intersection. It was originally video detection, we replaced it with video detection, and we had to look at a cost-effective solution to meet all the needs that we were trying to get at to feed all the data into ATSPM.
And you've seen earlier in the Purdue coordination diagram, basically the fruits, right? The hard-earned fruits of this configuration. And in order to see actually how it is configured, I'll give you the pleasure of looking at this type of setup, again, with the caveat that the advanced detection is not necessarily the 300-foot margin. They're more like 200 feet. But for how large that intersection is, I consider it quite the achievement. Questions?
We have 1 dome.
The system does not allow.
Yeah, it's one of the things that we have asked for of the product vendor is, have they looked at a 2-dome camera, two advanced camera solution? Yeah, a 4-camera type solution. Mainly because in North Carolina, we're a wood pole environment, and everything is set back outside the clear zone. So I know my NCDOT brethren are back there. They go through the same growing pains. But you go to Virginia, and it's a very different solution. They're a metal mast arm pole organization. Every new traffic signal is metal. So it's a very different challenge between the 2 state jurisdictions, and then you look at the municipal jurisdictions and very different challenges there. So that's kind of what's quality about the product, is it meets the 2 needs, but we would like for it to go a little bit further so we could really take all that hybrid detection out and just do everything with video. And as everyone knows, if you're looking at iTerrace or Conalite or Trafficon or FLIR, any of those solutions, you're going to have a camera for extension to get 300 feet out. You're going to have a specific camera to get 300 feet out in 4 approaches, right? And then you've got to get presence detection. So we're now talking 8 cameras. And if anybody's priced 8 cameras out of a FLIR solution, you can kind of run the numbers in your head what that might be versus in a Conalite solution what that might be. And not to say anything bad about any of those solutions, but we're talking about spending dollars as a municipality when you're running out of general fund. And that's a difficult thing to try to manage.
So you mentioned the open source U.G. I'm familiar with that platform. Is that what you guys are using? Or
No.
Do you know how your detector system interacts with that? Like, can you speak to that at all?
So we're actually we've been actively using for the past 1.5 years a cloud-based ATSPM solution. So basically we pipeline, compress the data, and then send it to the cloud, and all the data is stored there. Because, again, I'm a computer engineer by trade, so for me, if you tell me that I have 4 to 8 kilobyte logs constantly from every single detector, you have 60 detectors, then you're running, let's say, a RAID 10 terabyte setup, 4 drives, maybe you can get, what, 2.5 years worth of data of it? So we'll already be running, you know, long at a tooth in terms of space with this.
Yeah,
So this was,
UDOT Solutions, what, 20 to 30 megs per day
yes,
per intersection?
yes, yes. So that's the other thing. This
Megs.
solution has a proprietary compression style algorithm that minimizes the packages in quite a way. And it's all stored in Azure Cloud. Well, we're happy to share, as Daniel mentioned, any configuration setup, any, you know, all the templates that we've created, and whatever other, we can honor whatever requests you guys would have.
Yes.
Yeah.
I will say that with GRIDSMART, with the open API, they've made it really easy to implement the SDK, the string, the IP string into pretty much any ATSPM software. It's one string of command that you put in, boom, that intersection, you're getting all your data right in.
Yeah, that's something.
GDOT, and it's rock solid.
That's something our vendor is working on as well, because GRIDSMART has developed an API. And with that API, a software vendor can interface with that API. And then if you configure it correctly in the GRIDSMART platform, it will automatically transfer over into the ATSPM platform, which is a lot of hours saved at the very beginning. Configure it in one spot, let it automate and trickle downstream to your software and start collecting data. Thank you all very much for your time.